It's finally here, the much awaited SPARCstation 5 Disk I/O Battle Royale. This project took forever. Has taken such an unanticipatedly large amount of work to get done. First, I had to spend about a week trying to get a C compiler on the system so that I could actually run the benchmarks that I wanted to run. That is a whole side story of its own. In the description, there will be a link to a GitHub repository that contains a bunch of the details about the process that I had to go through to get a compiler on the system and the steps that someone else could take to reproduce that without having to go through all the effort to figure it out on their own. And then once I was able to wade through that, I selected a fairly large number of disk configurations, and in each disk configuration I had to do about 2 hours of installing Solaris on that disk, and then running the benchmarks took probably on the order of 4.5 hours, because I ran each benchmark multiple times to get an average score. And anyway, it was a whole big process. In the end, I ran 2 different kinds of benchmarks. I ran a single synthetic benchmark. I chose Bonnie++ because it's a well-known UNIX file I/O benchmark. And then I also, the thing about synthetic benchmarks is they represent some sort of an idealized use case, but they don't represent any real use case, which makes them, they can provide you with some interesting information, but in and of themselves, they're not that useful. Don't ever make buying decisions based on synthetic benchmarks results, just as a general rule. So they provide some information, but then I came up with some specific application benchmarks based on how I anticipate I will use this actual system. And there's basically 5 benchmarks that I ran. The first was doing a recursive file search to search all of the files, all of the text files in a part of the system for a specific text string. On a modern Linux system, I would just use grep-r for this, but this is not modern by any stretch of the imagination, so I had to do it the old school way of using find to find all of the files that matched a specific pattern, and then pipe that to xargs, which will try to create a maximal length command line for grep to actually search the files. So this is kind of the beauty of Unix. You have a bunch of tools that each do one really simple thing, and they do it well, and you can combine them together to do some larger thing that the creators of the individual tools never would have anticipated. That's sort of the beauty of Unix. The next benchmark that I ran, so that previous operation is a really common thing that programmers will do when they want to find, like, in the system header files, where is this function defined? What header file do I need to include to get some function? Or I want to know the details of some system data type. Where is it? So it's a really common thing to do. The next thing I did was decompressing and extracting a large compressed archive file. In this case, the archive file that I chose was one that I had to use on every single disk configuration, because it was the archive that contained all of the compiler stuff that I had to build on the Linux system and then ship over onto the Solaris system to actually use. So that's literally a real world use case. And I ran that by running a specific build of gzip. So I had reproducibility there of always using the same gzip binary to decompress it and then pipe that output to tar to extract all of the files. So there's 2 kinds of I/O happening there. Gzip is streaming in a large sequential file and it's sending the decompressed data to tar that is then kind of splattering out a bunch of files of various kinds of sizes, because there's a lot of header files that are going to be small, a lot of library files that are going to be kind of medium sized, and then a handful of program binaries like the GCC binary that are going to be comparatively large. So it's a definite mix of kinds of file I/O that are happening. The final three tests were actual compiler benchmark sort of things. The first was compiling all of gzip from scratch. Just go through and build all of everything. Now, my expectation is that that's largely going to be a CPU benchmark, and that basically all of the time is going to be spent in GCC itself. But disk I/O may have some effect on the performance of that benchmark. The second compiler test is to use the touch command to update the modification time on a single file in gzip, and then run make again to rebuild whatever needs to be rebuilt. So this will do a lot of I/O to look at all of the files in the project, figure out what's been modified, figure out what things need to be rebuilt, rebuild the small set of things, and finish it up. So this is a really common operation that programmers will do while you're in the edit, build, debug kind of cycle. And it's the thing that sort of determines how efficient your workday is going to be. The final compiler test is to just run make clean, which is just going to go through and try to delete all of the build products that were created in the build process. So these are sort of real things that I have been doing on this system and that I intend to do in the future. So the performance of them actually matters to me. And that's a good way to make buying decisions, is find the stuff that actually matters to you and figure out how that is going to perform on the things that you're trying to evaluate. If you ask an engineer, and I drive my family nuts about this, whenever they ask me, hey, which one of these things is better? My answer is always, it depends. It depends on what you're going to use, what other hardware components you're going to use it with. It depends on how you're going to use it. There's a lot of variables that prevent there being a fixed answer to that. In most cases. Sometimes there's, a pretty clear and obvious answer, but it's actually pretty rare. All right, so let's go ahead and enough jibber jabber about what I'm going to run. Let's go ahead and just dig right on into it. All right, let's go ahead and look at the individual competitors in this great SPARCstation 5 I/O shootout. Ooh. We'll start with this Seagate Hawk ST31200WC drive. This is one of the drives that was originally installed in this system when I received it. I believe it's also one of the drives that Sun actually shipped. So this came from Sun. It's a 5400 RPM drive, 1.05 gigabytes. So it's pretty small capacity and pretty slow, even by spinning Rust standards. One of the benchmarks that I am running on these devices, the Bonnie++ benchmark, is unable to run on just this drive. The problem is Bonnie++ needs 300 megabytes of free space in order to be able to create all of its temporary files and do its stuff. And with the full Solaris install on here, there was only about 180 megabytes free, which is annoying. One of the things that I wanted to do anyway was, when I received this system, it actually had two of these drives. So one of the things that I wanted to do anyway was try some of the benchmarks with both of these drives installed, and just all of the operating system installed on one and all of the user files installed on the other, so that in particular things like the archive unpacking benchmark that I wanted to try. I would put the archive on one drive and unpack it out to the other drive, and the C compiler benchmarks, all the source code would be on one drive and all the object files would be written to that drive, and the compiler and the system headers and all that stuff would be on the other drive. So you could split up some of the I/O workload between the two devices and see how that would affect things. Unfortunately, as they say, mistakes were made, and this drive sadly got dropped, and now, and it'll take a minute to spin up, now it just makes sad hard drive noises. And then turns itself off and says goodnight. So while that drive is not able to be used, it turns out I had a third Seagate drive, ST31051N, which, as far as I can tell, is a pretty similar drive. The other drives have a wide fast interface, and this just has a narrow fast interface. I don't think that should have any impact on the SPARCstation 5, because the SCSI controller on the SPARCstation 5 is fast narrow, so having the other drives be capable of 16-bit transfers won't matter because it can't utilize that. It's the same capacity, 1.05 gigabytes. It's the same 5400 RPM. It's the same cache. There's maybe a difference in the version of the controller, that maybe those other drives could have a more efficient controller since they're enterprise drives, but I don't know. My expectation is that this drive will perform very similarly to the one that I broke. We'll find out in the benchmarks, though. Temporarily moving away from Seagate drives, but staying in spinning Rust, I also have this Quantum 2 gigabyte SCSI drive, FBSTS 2.1S. I'm assuming that it's 2.1 gigabytes unformatted and 2 gigabytes formatted. I don't know. Also a narrow device, also 5400 RPMs. I honestly expect most of the 5400 RPM drives to perform pretty similarly. This has a different amount of cache than the other drives, so that could have an effect on the performance of this. And obviously it's from a different manufacturer, so it has different controllers and everything else. So it'll be interesting to see how all of that plays out. Okay, I have a second Quantum drive. It's an Atlas II 9100S. This is a 9.1 gigabyte drive that I had been using for a while in an Amiga 2000, but it is loud and hot, and having to use the SCA to 50-pin adapter, it didn't fit very well and was kind of a hassle, so I haven't had it in any computer for quite a long time. It is a pretty fast drive, and considerably more capacity than any of the previous drives. Unfortunately, due to its form factor, even if this turns out to be the perfect drive for the SPARCstation 5, I can't use it in there. The way that the bracket for connecting SCA drives works, there's two connectors. One of the connectors is in the bottom, and the other connector is right about here, so it physically won't fit. And if I somehow put it in the top slot, well, it's too tall to fit in the case. And just like with the CD-ROM drive from a previous video, it's too tall to fit in the other side of the case, in where the removable media bay slot would be. So this can't fit inside this computer. So that's kind of annoying. But, just for doing comparing all the things, I'm going to go ahead and include it, even though I can't use it in the final build. Then moving even a little bit newer, I have this IBM SCSI drive, DDRS-34560. This is a 4.560 gigabyte drive from January 1999. This is a very fast drive, which kind of confuses me that it has a narrow interface given kind of the high-end nature of this drive. I found that very odd. I have another IBM drive that is very similar generation that I think is also from 1999, but it has a wide interface. I really wanted to test that drive in this computer, but I did not have any of the right adapters to be able to connect a wide drive to either a narrow SCSI or a wide drive to a SCA interface, so I just had to leave it out. I'm going to end up with enough things to test, so I'll be plenty busy. It'll be fine. This drive and the previous Quantum drive are 7200 RPM drives, so I fully expect that both of them will be considerably faster than the 5400 RPM drives. Temporarily stepping out of the realm of spinning rust, I have a SCSI to SD version, I want to say 5.0A. It'll have the correct model number in the overlay and with all the full device statistics. So this particular device, even though it's an SSD, is going to be significantly hampered by two factors. One, in this version, they use a very slow version of the SPI protocol to communicate between the controller and the micro SD card. And the reason that they use that is because the version of the SCSI interface that they use is the old asynchronous interface. And just like we found when we moved from asynchronous DRAM to synchronous DRAM, when you have both parties agree on a clock and certain things are going to happen at certain ticks, the entire protocol just becomes much, much more efficient. You don't have to do, I'm going to send a signal to say I'm ready, and then I'm going to wait to see if you send a signal that says you're ready, and then I'll do a thing. It's just when the clock gets to this point, a thing is going to happen. You better be ready. So cutting out all that sort of negotiation dramatically improved the efficiency of the SCSI protocol. So even 5 megahertz narrow synchronous SCSI is generally much faster than asynchronous SCSI, unless you happen to have two devices that are very, very finely tuned to each other and can be very efficient with each other. But in general, the asynchronous SCSI interface is not that performant. Now, the SCSI to SD 6.0, which I don't have, unfortunately, does implement the SCSI to fast synchronous protocol. So it's able to communicate at 8 bits wide, 10 megahertz, and it's my understanding that they are much, much more performant. It would be very interesting to test out that device in this computer to see how it does in these benchmarks. It should do great, but I don't have one. Maybe someday I'll give that a try and see how it compares. I'm fully expecting that this is going to end up going right back in my Amiga 3000, and it's not gonna live in here. But we'll see. The final contender, it's really hard to even present this drive with a straight face, is this, again, back to spinning rust, back to Seagate, but this is a Cheetah 10K RPM drive, model ST3146707LC. This is a 146 gigabyte drive that implements the Ultra SCSI 320 interface. So it's capable of talking a language that this computer cannot even dream of. There are other SCSI controllers that can be added into this computer, but even the most advanced ones are not capable of getting the full benefit of the protocol that this drive can use. No one could have even dreamed of a drive like this existing when this computer was made. You would have needed a big stack of drives to get this kind of capacity. Not only is it 146 gigabytes, but it's 8 megabytes of cache on the drive, which is ridiculous for this computer. This computer only has 16 megabytes of RAM. So, given the massive I/O potential of this drive, the massive amount of cache, the ridiculous RPM, I kind of expect that this drive is going to completely blow away all of the other drives, but we'll see. So much to my surprise, even though this is a 10K RPM drive, it's very quiet. It does not, I have turned it on and made sure that it works. When it's inside this case, I can't hear it. Several of the other drives, including the drives that were originally shipped with this computer and the extra tall quantum drive, are super loud and I can hear them. But this drive and a couple of the other drives, the fans in the power supply are louder enough than these drives that they don't appreciably add to the overall sound level of the machine. So there's a good chance that this will be what ends up living in here, but again, we'll see. Now, even though this is capable of a much more advanced version of the SCSI protocol, one nice thing about SCSI, like USB, is that newer, more advanced devices are capable of dumbing themselves down to talk to more primitive hosts. So, for the most part, this drive should be 100% compatible with this computer, and it should just work fine. Now, that has turned out to not quite be the case. As far as I can tell, though, all of the difficulties with this drive are entirely software problems with the operating system that I have chosen and the system tools that come along with it. If I were using a more modern version of Solaris, I fully expect that none of the problems would happen. But rather than just being vague and kind of talking about the problems, let's actually go take a look at how this drive works in this system and the difficulties that I encountered. So up to this point, I've just taken all of the defaults for everything and just going to try to do a regular plain old install like I've done on all the other disks without any difficulties. But this is where the Solaris hits the fan, so to speak. It tries to create the file systems, and then the whole thing just craps out and dies in a fire. So the problem is, I'll make this window a little bit bigger. If I say, so the installer runs a program called NewFS, which runs a program called MakeFS, which is the usual thing that you would still use these days on a Linux system to format a partition to some kind of a file system. So we'll do dev rdsk Caesar. Now this NewFS program is supposed to make things a little bit easier on you by picking a bunch of sensible defaults for things. These old Unix file systems are tuned so that they really want to know where things are physically on the disk, so that it knows where the directory tables are and a bunch of other things like that are going to be physically on the disk, so that when it's scheduling I/O operations, it can optimize the order that I/O is scheduled based on where the drive arm is moving on the disk. As the head seeks back and forth, it wants to try to, if I'm going this direction, if the head is here and it's going to here,
is there some I/O that I can schedule in the middle to try to optimize performance and minimize the seeks? All right, but this kind of backfires on us here because it gives these values that NewFS figures out, all right, I'm going to tell MakeFS these values, and MakeFS says, no. Those values go against the internal rules. You can't do that. And so then the whole thing just falls apart, and the install completely craps out. So you can manually run MakeFS at this point and tell it the correct values that it wants and make it happy. But when you rerun the installer, it's going to try to do that again, and it's going to die at this same point. So the trick that I'm going to try is I'm going to use format. There's one other thing I have to do first. I'm going to use format to basically lie about what the disk is so that then everything else will be happy. But first, it's already gotten far enough along using this disk that it's set up swap on this disk, so I have to turn it off, or the format command is going to complain at me. You can't do that while the disk is being used for swap. Well, thanks. All right. So disabled swap on it. So now we can do the format. There have been a bunch of times that I've tried to do the format without turning off swap and went through all the work of setting everything up the way I wanted and had it say, oh, hey, sorry. All right. So the first, the partitioning, or the sort of the basic setting up a partition table so that the disk can be partitioned is done by the type command. Now, you would think you can just say, oh, auto-configure, it will sort its life out. And if the disk is completely like zeroed out when you boot up, it will try to do this as part of the install, and it will fail because this disk is apparently just impossible as far as this version of Solaris is concerned. All right, so we'll try again. And this time, what I'm going to do is I'm going to say other, and I'm just going to make a bunch of stuff up. Now, the stuff that I make up is going to be, if I tell it the actual values for this drive, like I want to say this drive has 90,744 cylinders, it says no. And in fact, the maximum value is what can fit in a 15-bit value. All right? So, okay. So I've picked some values that are not the actual values, but that end up being the same capacity for the drive. So I'm going to do 30,248. And then the number of heads, there's actually 4, but I'm going to say 48 because that makes things work. And then sectors per track, 197. Tell it that it's a 10K RPM drive, and then take the defaults for everything. And I'll just call this disk type name ASDIF because it doesn't actually matter. And then what is the next thing? Label. Okay. And then I should be able to say, and look at the default partitions. And so this is close enough to the actual size of the disk. It's a little bit less, but it should work. Right. And then, so label already wrote all that, so I should be good to go. And now I should be able to just restart the installer, and it should just work. Ho, ho, ho. So this will take a while. There will almost certainly be a cut here. All right. So back in the install, let's just take all the defaults again. Install all of everything. Already picked that. All right, this is where it was before, right when everything went south. Great success. Okay, so I'm going to return in 2 hours or so when it's actually done creating the file systems and installing all the stuff on the disks, and then I actually won't even show the rest because it's just going to be running the benchmarks that I'm talking about. But this is what I had to go through to get this modern disk, which is without a doubt the fastest disk on paper that I have. When I return, the great performance comparison will begin. It's finally time to actually look at some of the data for the benchmarks. This graph is the result of the Bonnie++ synthetic benchmark. It is measured in terms of work units performed in a certain amount of time, so larger values are better. I have chosen to normalize all of the results to the performance of the dual ST31200WC drive configuration. I would have normalized it to the single drive configuration, but as I previously mentioned, I was unable to run this benchmark in that configuration due to insufficient free space. Most of the data in these results pretty much matches what I had expected, but there are a couple of interesting things. One, in a lot of the tests, the SCSI to SD performs very, very poorly. The put block test and the get block test, the performance is absolutely terrible. And likewise in the read-write test, it is terrible. It's about a third of the performance of the original drive configuration. And I don't have a good explanation for that. I don't really know enough what those tests were doing to be able to formulate a reasonable hypothesis about that. The SCSI to SD also performed fairly poorly in the PUTC and the GetC tests. Somewhat surprisingly, the 7200 RPM IBM drive also performed very poorly in those tests. Now, those tests are basically modeling a Pessimal application that is doing a large amount of I/O using the PUTC and GetC functions, which read and write a single byte at a time. These are intended, I think, to largely be CPU benchmarks and to see how good the underlying operating system and C library are at coalescing reads and writes and trying to optimize small reads and writes. And in both of these tests, the CPU was pegged at 99% utilized. So I'm a little bit surprised that they perform so poorly. My hypothesis about the SCSI to SD is that in these particular tests, there's a lot of command traffic and very little data traffic on the bus, and just all of the handshaking to send a ton of small commands just overwhelmed the asynchronous bus implementation that the SCSI to SD uses. This seems a reasonable hypothesis, but that doesn't provide any explanation for why the IBM drive performs so poorly. As expected, the 10K RPM Seagate drive just owns. Across the board, it just owns. I mean, there's a few benchmarks where all the drives performed basically the same, and then ones where there's, any difference in the drives. I mean, that 10K RPM drive just rocks. Even at the Seek test, in the Seek test, the 10K RPM drive is almost twice as fast as the SSD that doesn't actually have to do any seeking. Now, this is another test where I think the SCSI to SD version 6 would perform a lot better because, again, it's probably very much overwhelmed in command traffic. I have a suspicion that the 10K RPM drive is doing an additional optimization. I don't know exactly how the seek test works, but I suspect that it's trying to make the drive do a bunch of seeks and then either do a tiny I/O or not do any I/O at all. And the drive is either reordering the operations or it's detecting that there's multiple seeks without reads or writes in between them, and it's just dropping those other seeks on the floor. Like, you told me to move the head, but then you didn't try to read anything from there, so I'm not going to do that. And I know that, for example, OpenGL graphics drivers will do that if there's multiple state commands in a sequence and there's no drawing operation that happens between them. Some of those state change commands can just get elided. I know that because I've implemented some of that code. So I suspect that it's either dropping spurious commands or reordering the commands itself to be more optimal, and that explains why it's just so much faster. Moving on to the real-world application benchmarks. Like the previous graph, this graph is normalized to the performance of the baseline configuration. In this case, that is the single ST31200WC drive. Unlike the previous graph, this is measuring time taken to perform whatever the particular benchmark operation was, so a lower value represents better performance. Now, every configuration outperformed the baseline configuration with one exception. And I think this is part of what throws off some of the results in the previous graph. So the one exception is the dual drive configuration running the make clean test. Now, what makes this test different from the others is that this test pretty much just exercises the performance of whatever drive is storing the user's home files. So this is the test where it's going through trying to find all of the build products from compiling gzip, so all the object files and everything else, and deleting them. So it's just heavily exercising that disk. So this leads me to believe that my initial hypothesis that both those models of Seagate drives should have very similar performance was probably false. And so that kind of throws off everything about trying to draw any conclusions from that dual drive configuration, which is a bit of a bummer. Nonetheless, the dual drive configuration did outperform the single drive configuration by at least a little bit in all of the other benchmarks. So that definitely supports the hypothesis that spreading the I/O workload out across multiple drives so that the operating system can do smart things about the scheduling of those operations and whatnot. I mean, that absolutely is valid. And that is definitely a thing that people used to do on these kinds of Unix systems back in the day, is configure multiple drives and spread stuff out across them because it does improve performance. So the other thing that's a little bit surprising here is how well the SCSI to SD performs. From the previous graph from the synthetic benchmark, I did not have very high expectations of it, but it performed pretty well. I mean, realistically, in the recursive file search operation, the rgrep test, it had the best performance, which that test is going to do a lot of seeks and accesses to the directory structure and reads of small files. So it's going to be very seek heavy. And so that is definitely a case where an SSD should outperform any kind of spinning rust. I was really surprised that the second best performer in that is the 5400 RPM Quantum drive. Not only is that a low RPM drive, but if I remember correctly, it has the least amount of cache. So that is a little bit surprising and confusing, but I'm really not sure what to make of that. But in every other case, the 10K RPM drive was significantly faster in the make clean test where it's doing a lot of deleting of files and accessing the directory structure and a lot of small reads and seeks, the 10K RPM just crushed. In the other C compiler tests, the make all and the rebuilding a single file, or rebuilding after a single file had changed test, the make single, everyone performed about the same. And looking at the CPU utilization data, all of the drives were hitting over 90% CPU load, and almost all of that CPU load was in user mode, so it's all time spent in the compiler itself. Very little of the time was spent waiting on I/O, which means that, there is quite a bit of disk I/O that's happening, but the operating system is doing its job well, and it's overlapping the I/O operations with the heavy CPU operations. So the system's working the way it's supposed to. The other case where the 10K RPM drive was super, super fast compared to the others was the unpack test, where I had one process decompressing the file, and then a separate process was extracting out the archive and writing all the data to disk. I suspect that the 8 megabyte buffer on that drive made a huge difference there by making it so that, and this supports my other theory about the reordering of operations, that large buffer allowed it, as it's streaming data in, stream a whole bunch of data into the decompression process, and then as it's writing data out, buffer a bunch of those small writes and reorder the seeks and the I/O, the read-write operations to be more optimal. So the large buffer lets the drive do a bunch of its own optimizations. Man, that drive just performs outstandingly. I'm super, super happy with the performance of that drive.
That was a lot of work. It was way more hours than I had anticipated spending on this project. But, in the end, it was kind of fun, and I think I got a lot out of it. The final result, my conclusion, I think I'm going to go with the 10K RPM Seagate drive. I think for me, for this system, that's the best choice. These drives can be had on eBay for, currently, drives very similar to this can be had on eBay for less than $50. They work properly with some effort on this kind of a system. So I think that makes it a really good choice. Now, SCSI to SD and some of the other competitors are still really great choices for older retro systems. I had that SCSI to SD in my Amiga 3000, and it was great there because I can use a single micro SD card to look like multiple SCSI drives of the maximum capacity that system can handle. That system would not even be able to deal with a 146 gigabyte drive. It would have to cry itself to sleep every night. So I think that's what I'm going to stick with. So I'm going to put I left it in the little plastic mounting bracket. I'm going to put it back in that system and bundle it up. And for now, I'm going to be done with these SPARCstations for a bit, and I'm gonna move back onto working on the new AT&T PC 6300 that I acquired over the summer, and I'm gonna play with some other toys for a while, and I'll be back with that in DOScember. So until then, try to remember the good stuff.